Hello everyone, welcome back to this channel. My name is James. I'm a computer science graduate turned teacher. In this video, we're going to look into chapter 13 of A-level computer science, data types and structures, which is the preparation for you to learn programming. And the big picture for this video, we'll first explore what data type is, and we'll explore the various data structures like array, record, abstract data type, so on and so forth. Just a reminder, if you like my videos and you have not subscribed, do subscribe so that we can hit 30% at the end of next month. And that will be the only favor I ask from you. Thank you so much for supporting. So let's look into what data type is. A data type in programming defines the type or nature of data that can be stored, manipulated, or processed. Basically, we are telling the computer what is the type of this data. Is it a character or a number? Because as we learned in chapter 1, different data needs to be represented differently using binary. Character use ASCII, numbers are just, you need to do the binary conversion. So data type is important for the computer to know what type of data is this. And we have two different types of data, primitive and further data type. So primitive data type is what we call the basic data type. For example, like integer, which is, it represents whole number, real, decimal point, boolean, a value that's either true or false, character, a single character. Whereas further data type is a type of data that derive from primitive data type. For example, string, which basically means a sequence of character. Underlying, it is still character data type, but then you combine multiple characters, it becomes string. Same goes to date, as number plus string if you put the dash. So that's further data type. The next data type I will show you is what we call the record data type. This is special because it is not built into the computer. It is user defined. And for example, if I want to create a record type called product, so it could potentially contain these information. So product could have a name, price, expiration date, whether it is a diary product. And as defined, the record type is known as user-defined type because the programmer can decide which variable to include as a record. And this is how we do it in pseudocode. By the way, if you have not learned about pseudocode, please watch my chapter 12 video because that is the foundation video for this video. Thank you. And that's how we do it. Type, what is the type identifier? And then what are the fields within the type? An example would be type product. And the product should have a name, price, and you can see that I already declared the data type of these fields. And this is how you declare a record data type in your program. Let's say I want to declare a new product called milk. And I can just write declare milk, the name, ... and what the record is. For now, we'll just forget this for a little bit. We'll look at it again when we look at linked list. So stay tuned. And this is how you can assign a value to the field in the record type, like Dutch lady, product price, expiration date, and whether they are diary. Now, let's look into the most commonly used data structure called array. And in the last video, we learned that we can assign a value to a variable, but then that is a limit because you can only assign one value to it. But what if you have a variable called student list? It's a list, right? You need to store a list of students' name. That's when an array comes in. It's a set of ordered set of data items, usually of the same type, grouped together using a single identifier, using a single name. So for example, I have this array called student list. That's the identifier. And within this identifier, I have multiple items in it. And these are all the names that is in the class. And what you need to know about array is that there is an index to specify the location of where the item is in the array. And there's also a lower bound and upper bound, which determines how big the array is. This is how we declare it in pseudocode. Declare keyword, the identifier, meaning the name, array, what's the lower bound, what's the upper bound, and what is the data type of the data that you are storing in the array. For example, if I want to declare two array like student list and student mark, student list, I will declare with the identifier and the upper bound and the lower bound, and the data type has to be string because I'm storing name. And in contrast, if you look at student mark, because I'm storing their mark is a number, therefore when you're declaring it, you need to specify the data type, which is integer. And now let's learn how do we access and populate an array. So we can follow this syntax, whatever the identifier is, followed by square bracket, and then a number. For example, in my student list array, if I were to do student list, the identifier, square bracket 2, I assign it to have a value of Ali. This means that Ali will be put into this location, which is of index 2. And this is how you assign a value to a slot in the array. And let's say I want to create a multiple of 10s array that has 10 value. Multiple of 10s mean 10, 20, 30, 40, 50. Then how do I populate it? If you have watched my chapter 12 video, you would have known that I can use an array, a list, a for loop. So, sorry, it should be you can use a for loop. So we first declare the array, how many slot it has, and what data type it stores. Let's define a variable called current multiple. And I will store this multiple into the first item, which is, in this case, index will be 0. And then I will increment the multiple by 10. And when next index occurs, this means that index is being incremented by 1. Now I'm going to move into index 1. I'm going to put in the value, added value, which is 20. So if we follow this loop, all the multiples of 10 will be added into this array. This is just a work example to help you understand how we can populate an array. Next up, in an array, a very frequent operation that needs to be done is called a linear search. Imagine that I have a list of students in my student list array. And I want to write codes that find whether a student name is within this array. For example, so linear search is a simple searching algorithm that can help me to do what I want, whether I can find a match. So this is the pseudocode, but I want to show you how it works. In essence, linear search will go through each item in the list until it finds a specific name. For example, if I want to find out whether Andrew is inside this array, I'm going to look into the first location, check whether it's equal to Andrew. It's not. Second, whether it's equal to Andrew. It is not. And the third, oh, I found Andrew. And the algorithm will then return true. Yes, I found Andrew in this array. And if it couldn't find anyone, let's say I put the name given is James, and the algorithm will look through each item in the array and found out that, oh, there's no James in this array. And what it will do is that it will let the user know there's no James in this array. And this is how we write it in terms of code. So we set out what is the upper bound, how big is the array, so that we don't go out of bound. And input name given, what is the name you want me to find? Create a variable called found, assign it to false, and index 0. So what happened is that we use a while loop while the name is not found and the index is less than or equal to upper bound, meaning we are not reaching the end of the array. I'm going to do whether student list square bracket index. Remember, this is how we locate an item in the array. Whether it is equal to name given. If it's equal to it, found equal to true. If it's not, then I'm going to go back to the algorithm. I'm going to do it all over again because the condition of this while loop is to stop until false equal to true. And at the end of the day, at the end of the algorithm, if found is equal to true, I'll put value found at location index. Otherwise, I'll put value not found. And I think a good way to learn how to write algorithm is to, just write it on your own on a piece of paper to see whether you can write out the algorithm from scratch. Because if I were to do it in this video, it would take a long time and that might not be good for your attention span. So try to do it. So the next operation that can be done on an array is sorting. And the only algorithm we'll learn in your syllabus is bubble sort. In fact, when I was in uni, they teach us multiple ways of sort a number, but for your case, we're just learning one. And how bubble sort work is basically let's say you have a list of number in an array. After the bubble sort operation, you're gonna have a sorted list. And how it does that is that it repeatedly step through the list, compare adjacent element like this, and swap them if they are in the wrong position. And I want to show you in visual how this works. So let's say this is where we start. What the algorithm will do is that it will compare the first and second element. If the first one is bigger than the other one, then we do a swap. So in this case, 45, 32. Since I want them to be in order, if 45 is bigger than 32, I'm going to swap their position, which is what you see in this case. And the next step in the algorithm would be compare the third and second and third element, the third and fourth element, and we only swap if the previous one is bigger than the yeah, it's bigger. And we keep swapping. 70, 89, 99 we don't swap, and 99 and 0 we swap. So you can see that after one iteration, the biggest number is already at the end of the list. Meaning, have we sorted? No, we have not. All the numbers here are still unsorted except the last element. So this algorithm says that we need to repeat it until all the elements has been sorted. So after one iteration, the biggest value is already in the correct position, but that's not what we want. We want like in order. So this is why I will carry out all the steps here for many different iterations. So after the second iteration, 788 will be in this position. Third iteration, 45. Fourth iteration, 35. Fifth iteration, 12. And at the end, I will have a sorted list. So to do it in pseudocode, I'm going to break this down, do some decomposition to help you understand how I write the code. So because, look, this is what we do, right? We compare the first and second element. If it's bigger, then we do a swap operation. So this means that I'm swapping the items. And before I swap, I will compare whether number list j is greater than number list j plus 1, which is the next item. I'm going to do it from the beginning of the list to the end of the list. But again, we know that even if we run the algorithm one time, we still wouldn't have the complete sorted list. We need to run this for more iterations. This is when I put an outer for loop, and to ensure that this operation is run many different times until the list is being sorted. So try to pause the video and use the algorithm to sort a list an array that you have written down on your paper, and just go through the algorithm to understand it, because it requires a lot of thinking process. I'm just providing an visualization and an overview. So this is the intuition basically. After one iteration, the biggest number at the end of the algorithm, I will have the list sorted. Now, look, the issue here is that there's a way that the algorithm could do unnecessary operation. For example, after third iteration, you can see that the list has already been sorted. But then because of the way we write our code here, it's a for loop, meaning it runs for a fixed number of time. It will still run even after the list has been sorted. So we can make the algorithm faster by putting some condition in. So to tell our algorithm that, hey, if this condition is met, you can stop sorting it. And the criteria is that, look, if we found out that if we have gone through the whole of the inner loop without swapping any unit value, meaning we compare first and second, second and third and fourth, so on and so forth, and we found out that there is no swapping occurs. This means that all the value has been sorted, meaning we can stop the loop earlier. And to track whether any swapping has occurred, I just need to add one more variable, which is swap, a variable that contains a Boolean value, true or false. And if I were to do this, you'll see that initially I assign a value of false to swap. And if there's any swapping occurred, I will then set this swap to true. But then if, let's say, I go through the algorithm and no sorting no swapping has happened, meaning swap value will remain false. And this is when I can end the loop. Look, I'm using a repeat until. That means I'm repeating the whole chunk of code here until swap equal to false, which means that this loop will stop after we found out that there's no swapping occur in that iteration. So that's the essence of bubble sort. And now we look into the next part of the data structure, also very commonly used. It's an array, but it's called a two-dimensional array. I'm going to show you how to declare a 2D array, how to access a 2D array, how to populate a 2D array with a nested loop. Eventually, we'll create a Connect 4 game from scratch. So first of all, this is how we declare a 2D array. Very similar to how we declare a 1D array. It's just that now you have to define the lower and upper bound for the number of rows and number of columns. If I were to do this, declare board, array 1 to 6, 1 to 7 of char, means that I will have 6 rows in my array and then 7 columns in my array, and they will store the character char. To access a 2D array, and what we learned just now is that I can use a square bracket. In this case, it's the same, but then I need to give 2 index because I need to specify the row and also the column number. This is how I will do it. To populate a 2D array with 0, let's say I want to put 0 into it. I'm going to use a nested loop so that I can populate the array row by row. So this is how I do the population. And outputting is the same. If you want to output everything in the array, you can use a nested for loop. Just access the item in the 2D array one by one. So now, the exciting part, to show you how useful a 2D array can be, we're going to create a Connect 4 game. It's in your textbook. So let's look into how the code can work. By the way, this is Connect 4. For you, those of you who don't know, you can win the game when you have 4 in a row. So that's Connect 4. Connect 4 dots together. And to save your time, I have written down the pseudocode overview in my slide. And that's the overview. If you look at the core keyword, means that each line here is a procedure, a function. And then let's do it. It's going to be long. Let's do it one by one. Call initialize board. So to start off the game, you need to create the 2D array to store the, whether it's O or X, you know, the token. So as mentioned, this is how you create a blank board. You use a nested for loop, row, column, and you just put nothing into the 2D array. And next up, you will have to set up the game. In this case, I am not putting colors into it. I'm putting 0 and X for the 2 players, like what happened in tic-tac-toe. And a variable called game finish that contains a Boolean value to store whether the game has finished. And output board. So to create this game, you need to output the board for the user to see what's the current state, and then so that they can pick which row and column to put their token into. So again, it's a nested loop, nothing new. Now, that's when the game starts. While game finish equal to false, I'm gonna operate these steps. And for player make move module, meaning the player select which row and which column to put, there are a few sub-steps. We need a procedure that can let players input a valid column, meaning the column has to be 1, 2, 3, 4, 5, 6, 7. And if the user enter, let's say -2 or 100, we're going to ask them to enter again because it's not valid. So a sub-step within this is that we need to check whether the input is valid, which is what I just talked about, and a procedure that finds a free row. Because once you have chosen the correct column, you still need to pick, your program still need to identify whether this column is fully occupied. If it's fully occupied, then you can't put in a token. And then you also need to find out a free row. The idea of Connect 4 is that you can't just put, in this case, you have to drop the token, and this is the only free row in this case. So your program will have to find out where is the free row. And let's look into how we write the code. So we can split the player make move procedure module into two different substeps. First of all, we find out what is the valid column, and then we find out what is the valid row. So let's solve the column problem first. So in this case, the procedure of player chooses column will look like that. It will output, hey, it's your turn now, X or O. Please output a valid column number. So until we have identified that the column number is correct. Here's another procedure. Look, it's just a top-down approach. So we create another function called column numbers valid, and it will return a Boolean number specifying whether the column number is valid or not. And we'll start off with valid equal to false, it's not valid. And if column number is greater than or equal to 1 and column number is less than or equal to 7, which means that the column number is within range 1 to 7, not 8. Then the algorithm will check whether this column is fully occupied. For example, my column number is 2. Sorry, my column number is 1. And this will check whether if board 1, meaning this location here, because my number is 1, and I will just check whether the first item, is it a blank? If it is a blank, meaning it's true. Otherwise, it's a false, right? Because if there's an item here, meaning that this column is full, so I don't want you to put that. So we'll return the Boolean here, back here, and this will serve as a condition to whether the user needs to enter another column number. So once the user has entered a valid column number, then we'll just go into finding the correct row. Let's say 1 is blank, right? That means it is a valid column number, and now we need to find out where is the free row. In this case, it should be 2. So this is what our algorithm will do. We'll start off with a variable called this row equal to 1, and if this is equal to board this row, meaning 1, and the valid column 1 it's not equal to blank, then we'll do this row plus 1 and then end while, meaning I'm go down until I find a blank value. Like if it's blank, I'm gonna go to the next one to find out the lowest blank value in that column. Sorry if I make this very complicated, but eventually it should return 2 as the free row. Now we got our valid column, and when we have our free valid column and valid row, I'm gonna put in my column, my displayer's move here. So in this case, it should be 0 here. Now I will output the board to let the user see, and the algorithm will now check whether the game has finished. And how we know whether the game has finished is whether the player has 4 in a row horizontally or 4 in a row vertically. So this is what I want to do. In check game finish, I will check if the player has won. That's another procedure. So let's look into what this procedure wins. I will check whether horizontal line has 4 connected, and the vertical line whether 4 items are connected. So let's look into the check horizontal line procedure. I've written it down to save you time. And let's look into this highlighted row. Let's say I put X here. And in order to know whether the user has won, I need to check whether the 4 items here, they are all equal to X. If you look into my algorithm here, I only check for I to 1 to I and 4. And I will look at the same row. Look, same row. And if the 4 of them are the same, if blah 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 equal to this player and equal to this player, then return true. But then in this case that I'm showing you, you can see that board, this is not X, meaning the criteria won't fulfill. And this is when I will return false. The user has not won horizontally. But it doesn't mean that it hasn't won vertically, right? It can be a straight line. So I'm gonna check the straight line again. Check vertical line, and if valid row equal to 1, 2, or 3, meaning if the user has entered a token somewhere around 1, 2, and 3, only I will check. Because if the user were to enter a location, let's say in this spot here, then he couldn't have possibly win because everything up there is empty. So this is why I'm only checking valid row 1, 2, and 3. And I will check whether the 4 of them, 2, 3, 4, they are the same. And in this case, they are not. That's why I'm going to return false. And the winner found here will contain the value false, meaning the user has not won yet. So hopefully this makes sense. And next up, if game finish equal to false, user has not won, meaning it's now the other player's turn. I will call the stop this player procedure, meaning if this player is O, I'll change this to X, otherwise I'll change this to O. And this program will run repeatedly until we got a winner. So feel free to just rewind from the beginning, because this is a very difficult question. Just watch for a few times if you are stuck. Look into how I write this code. And yeah, try to write it from scratch if it can help you to understand how a 2D array can be used. Because in this example here, we have seen how to create a 2D array, access a 2D array, an item in a 2D array, and also how to show the content of a 2D array. So this is a really good example from your textbook. Now let's look into text file. Text file is not a data structure, but then sometimes when you're programming it, it will be very useful. Basically, the text file stands for txt file, and we need it when we want to write the value of a variable in a program into an external file, or we want to read the content of a txt file into our program. So this is why when it comes to text file, we'll look more into that in chapter 14, but for now, just learn the syntax first. Pseudocode. This is how we open a file for writing. Writing to a text file means I want to write something from my computer program into an external file. Open a file. What's the file name? For write, to specify whether it's a read or write operation. Write file, whatever string value you want to read to it, and then close file. Same goes to read. The only difference is this keyword here, whether you are reading. Reading a file is the opposite. When it's happened when you want to read values from a txt file into a program. Let's say you want to store it in an array. So that's when you read it. And the third operation you can do is called appending. Let's say you have an existing file, you want to add a line to the txt file. This is when you can use the append keyword. And lastly, you need to know what is the end of file marker. It is a condition or marker used in programming to indicate the end of data in a file. So this indication will help the program to know when to stop reading files. So let's say I'm opening a file called test.txt for reading, while not EOF, so this is a function, means that if I haven't reached the end of the file yet, I'm going to read out the line in the txt file and I'll output the text file. And wow. So at the end of the day, I will just close the file after finish reading everything. I think it will be clearer when I show you how to do it in chapter 14. So stay tuned for that video. This is just a pseudocode. Now let's look into the last part of our video here, abstract data type. This is something I learned in my second years of university. And the three abstract data type you'll be learning is stack, queues, and linked lists. Think of them as an alternative to array, and they operate differently as well. Let's look into stacks one by one. A stack in programming is the data structure that operates on a last in, first out basis, allowing data to be pushed and removed from the top of the stack. So I have a stack of books here. Just think of this data structure like when you're stacking books, the first book that you put into the stack will be the last book that you take out, for example, in this case. And the last book that you put onto the stack will be the first book that you will take out. I mean, given that you don't just take out from here. And that's the intuition of a stack. And I can use an array to represent a stack. So I will show you how it works. In the stack, I have a base pointer, meaning a pointer that contains the value on the base, and a top pointer, which is always assigned to a value called -1. And I'll show you how to add item into it. So let's say when I add the value A into my stack, top pointer will be incremented by 1. And base pointer will not move because that's the base of the stack. And every time I add an item, the top pointer will move one step forward. Move, move, move. And that's when you add an item to the stack. But what if you want to remove an item from the stack? You can't remove item A because stack operate on a last in first out manner. So the item that we'll remove first will be E. And in the stack, when an element is removed, top pointer will decrement be decremented by 1. And so this is the function of last in, first out. The last item that's added is E, and the first item that's removed will also be an E. Now, that's stack. It operates on the last in, first out issue. For queues as well, think of this as the normal queue that you see in the McDonald's or a casual. It operates on a first in, first out function feature. So a queue in the programming is a data structure that follows the first in, first out principle, FIFO, allowing elements to be added at the rear and removed from the top front of the queue. So let's look into it. Again, when you're implementing a queue, we won't do it now, but then you will learn how to do it in chapter 20 plus. But for now, just understand what are the components in the queue. You have a front of queue pointer, and you have an end of queue pointer to point at the first and the last element. And when you add an item to the queue, the end of queue pointer will move. All right, keep moving, keep moving, keep moving. So you can see that now front of queue pointer is pointing at the first element, end of queue pointer is pointing at the last element. And let's say you want to remove the first element. So once A is removed, all the item will have to shift one step forward. But of course, we will learn that it's actually not needed, the swapping. So you just move up. And the end of queue pointer will be decremented by 1, if you see. I just move it one step forward in this. But even if this method works, it's not very efficient because it involves a lot of data shifting. Because if you have 1 million items in your queue, you have to swap 1 million times. That would take a long time. So that's when circular queue comes in. A circular queue does not involve data shifting. Instead, only the pointer change. So the same scenario, if I were to remove A, instead of moving every item up, I only move the pointer. Look, it's a lot more efficient. And when I add item to the queue, I just keep incrementing the end of queue pointer, keep adding. And eventually, the queue will wrap around from the beginning. But it doesn't matter how the items are arranged here because I already have a pointer that shows me where is the front and where is the end of the queue. So that's circular queue. And the last abstract data type we'll explore is linked list. And let's look into what linked list is. A linked list is a linear data structure where elements known as nodes are connected via pointers, each node containing data and a reference to the next node in the sequence. So this is the node, and the node contains data and the reference to the next node, meaning where it's pointing to what's the next element. So we also have a start pointer, a variable that stores the address of the first element of a linked list, or point to the first node, and the first node will point to the second node, second node will point to the third, and the last node will point to something called a null pointer, a pointer that does not point at anything, which is usually a none or blank in pseudocode. So let's look into some of the operations you can do on linked lists, and hopefully after the end of this introduction, you will see how powerful a linked list can be. So we'll only do these 6 operations. Let's insert at the beginning of the list. Let's say I want to insert a new node into the beginning of the list. What I need to do is just copy whatever the start pointer is pointing to. So the start pointer is pointing at this, to the new node's point of view, meaning here. So I'm going to click. So whatever the start pointer is pointing to is now in the reference of the new node. And the start pointer will now point to the new node. And then this is how you add an item to a linked list at the beginning of the list. So if you want to insert at the end of the list, it's even simple. We just let the last node, we connect it. Instead of connecting it to the null pointer, we let it connect to the new node. And the new node will connect to the null pointer. And that's it, inserting at the end of the list. I think the most complicated one is to insert at the middle of the list, but it's not that hard. Let's say I want to insert B in between A and C. All I need to do, so now A is pointing at C, I'll just copy whatever node A is pointing to. I'll let B connect to point C, and let A connecting to the new node. So if you can see, it's very efficient because every time you insert an item, the only thing that you need to do is to change the pointer. Change the pointer of this and change the pointer of this, and you have a modified linked list. and that's very efficient. So let's look into delete. Delete is very similar. If I want to delete everything at the beginning of the list, all I need to do is copy whatever node it's pointing to, copy this link, to let the start pointer point it. So let's see. So this is how I do it. And now A will be fully disconnected, and it means that I have already deleted the item. And if I want to delete at the end of the list, simply pick the last two node and let this previous node point to the now pointer. So this is why when you're implementing it in Python or pseudocode, you will need a variable called previous node so that you can directly let it point to the now pointer. So delete at the middle of the list. Let's say I want to delete C. I'll just copy whatever node C is pointing to point A. Ta-da! This is how I delete something at the middle of the list. So why is linked list preferred? The utilization of pointers enable efficient insertion and deletion by solely adjusting reference between nodes, eliminating the necessity for frequent data shifting. So this is something I talk about. We only need to change the pointer values to change the location or delete something. Of course, one disadvantage is that we need extra storage to store the pointer. I'm going to show you how to implement it in an array, but then of course this is not the ideal approach. Just think of it like learning how to implement a linked list using an array. Okay. So as you know, a node contains data and pointer, and we only need to create another variable called start pointer and point to it. So let me give you an example here. Let's say this is my linked list in diagram view, and this will be how it looks like in array view. My start pointer will point at the first element of the linked list, which is x. So this is why you can see start pointer contain value 2, meaning it's pointing to 2, which is x, and x is pointing to 0, which is y is pointing to 1, which is z is pointing to -1, which represent the now pointer. So let's say I want to add the node w to the beginning of the list, and I want you to see the only change we need to make. Look, if I were to add w to it, meaning that the only change I need to do is to let the start pointer to point it at w, which is 3. We just change the start pointer from 2 to 3, and let w be the value of start pointer. So in a blink of eyes, so start pointer is now pointing to 3, and w is pointing to the value that the start pointer was pointing initially. So you can see that I only need to change 2 values here in order to add an item, which makes this stuff really efficient. And the same goes to the end of the list. So you can see everything is pointing. Initially, Z is pointing to -1. All I need to do to add a new node at the end of the list is to let the new item point to the now pointer and let Z point to the new items that I created. So it means this will be turned to 3. This will be turned to -1. 3, -1. Same goes to deleting it. So deleting it, I only need to change one item. Now start pointer is pointing to 2, but let's say I don't want it. I can just change the start pointer value to whatever x is pointing, which is 0. So look, start pointer, change to 0. One catch is that the old data will still remain in the array. We'll learn how to make it more efficient later. But then know that at this point, even though they are in the array, but they are inaccessible because no one is pointing at x, no one is pointing at 2. So we can say that they have been deleted from the linked list. So deleting the last element is the same thing. Whatever z is pointing to, I'll let y point it to. So y will be pointing to -1. So hopefully this method of teaching helps you. You can see diagram view and array view at the same time. Now, a free list pointer is utilized to manage available unused space in an array that can be used to store new nodes. Because if you look at this diagram here, even if a z has been deleted from the linked list, but it's still in the array, they're taking up spaces when we don't want them to. So this is when I keep a free linked list to keep track of which position can I use to store the new node. And to show you in visualization form, let's say this is an empty linked list that I've created, and then I add z, x, y, but I kept it in alphabetical order, which is x, y, z. Can see that start pointer is pointing at x is pointing at 2, which is y is pointing at z, etc. And imagine that I delete, let's say X is deleted, meaning that now the position that X occupies should be available when a new node is added. So I'll just connect this, and now you can see that it's very useful. So start pointer will now point at Y because X is deleted, and then I will let free list pointer to point at the nodes that has just been deleted, which is X, pointing at that, and X will point at 3 instead. So if we were to see, now you can see that the free list pointer here is pointing at a node that is freely available because no one is pointing at them. So by just adding one more pointer, the algorithm will know which space we can use when a new node is added. So that's the idea of a free list pointer, to point at an unused or available spot so that we don't waste any space when we are using the linked list. Of course, to end this video, just to have a recap, if you remember, record types is a user-defined data type, and it can have many fields that the user want. To implement the linked list more efficiently, instead of using two arrays, we can actually create a record for it. We can just define the first field as data, which store the data, and the pointer as having a node data type, record type. So this is also what we will look into when we implement a linked list in Python, but it's not the scope of this video. This video is merely to introduce how a linked list looks like. And if you watch until this part, thank you so much for watching. I will see you in the next video when we look at the introduction to programming. Goodbye.